All right, welcome back. So we're now turning to the problem of if we're dealing with a graph in polar coordinates, let's apply the different calculus concepts that we've talked about in the past. In other words, uh, how do we do the slope of a tangent line, right? The slope of a curve at a point, right? So that's going to be one problem. And then the other problem is, given a polar graph, what if what amount of area is contained in a certain section of that graph or inside the whole graph? So either way. So that becomes our two questions. And we're going to focus first, excuse me, on the question of slope of a tangent line. And so that's our first problem. And at first you might think, how do we do that? Because these things are in terms of r and theta, right? And slope is in terms of x and y. So as we begin that, you might start thinking, well, how do we do that? So we want to talk about the slope of the tangent line. And so the key idea here is when we're given these polar functions, we're often given them as a function of theta, r equals something involving theta. But to talk about slope, we need to talk about x and y. But we can recall that we know that if we have r and theta, then we can convert those over to x and y. Right? X equals r cosine theta, and y equals r sine theta. So what we do is, using this idea, we create parametric equations for x and y. And that's the key idea here. In terms of the parameter theta. And so that's one of the reasons we even took time to talk about parametric equations, is because we can use them now to talk about how to find the slope of a polar curve. Because a polar curve can be parametrized into rectangular coordinates using the relationship x equals r cosine theta, y equals r sine theta, where r is some function of theta. So in other words, x is equal to f of theta cosine theta, and y is equal to f of theta sine theta. Okay. And now the way this helps us is that we've already talked previously now, just very recently, about how to do the derivative of parametric equations. Remember, the idea is that we take the derivative of the y function over the derivative of the x function. Right? And that's how we find the slope of the tangent line at the point f of t, g of t, is we take g prime of t, the y derivative of y, over the derivative of x. Right? Except now, instead of t's, we're dealing with theta as our parameter. So the exact same idea applies here. We just need to take the derivative of y over the derivative of x. So recall, we'll say here, recall, for parametric equations, that dy dx is dy d theta. It was dy dt, but actually, I'll say it this way. I'll say dy dt just to stay consistent with what we did before. Dy dt over dx dt, right, where t was our parameter. So that means for our problem, our derivative for our polar curve will be the derivative of the y function with respect to theta. So the derivative, in other words, of f of theta sine of theta. But f of theta sine of theta is just a product. So f of theta times the derivative of sine theta, which would be cosine theta, plus sine theta times the derivative of f. So that would be f prime of theta sine theta. And then all of this is then divided by the derivative of the x function. So the derivative of f of theta cosine of theta. That would be f of theta times the derivative of cosine theta would be minus sine theta plus cosine theta times the derivative of f. F prime of theta cosine theta. And then I'm just going to do a little bit of rearranging of things. F prime of theta sine theta plus f of theta cosine theta divided by f prime of theta cosine theta minus f of theta sine theta. Now there's no need, you don't have to rewrite it this way. And in fact, I would encourage you not even to memorize this, but just to remember that this comes from the product rule applied to both numerator and denominator. So I wouldn't memorize this formula, I would just remember how to derive it. Right? But it's definitely worth having, so if you're going to be using it, it's worth going ahead and deriving it first, and then having it to use, where again, remember, r is equal to f of theta. Okay. And so this formula will give us the derivative. Right? This formula will give us the derivative, or sorry, not the derivative, the slope of the xy function, or the xy graph, the derivative of the xy graph. Okay, at that given theta value. Okay. So this is the derivation of it. We're going to look at a couple of examples, putting it into use in some of our upcoming videos.